come into a little more detail later because this word non-simultaneous has to be explained by me. It's just that the transmission and reception can only happen on multiple links. Either transmission or reception can happen, but both TX and RX cannot happen. But we will discuss that in detail in the next few slides. There is also another type called EMLMR, and this one is very similar to MLMR STR, but with the word enhanced, which actually implies that it can also switch channels based on the antenna diversity that it is capable of. We would again discuss why this is called enhanced in the next few slides. Let us go to the other types of MLO that are also important. So we have the simplest form of MLO, which is called multi-link single radio MLSR. So most of the devices would be actually MLSR. So this is a very simple device. It has only one radio and it switches between each of the channels or links in some way. And this we will discuss later in the presentation. We also have what is called EMLSR. This is an important addition into the spec. Again, the word enhanced here implies that even though it is a single radio, it kind of exploits the transmit diversity to receive control frames on the other antenna. So this actually makes it work well in some scenarios and helps to achieve lower latency. And hence this new type EMLSR was introduced in the specification. So we would discuss now each of them in a little more detail, the theory part, what it is supposed to do. The first one is MLMR STR, simultaneous transmission and reception. What does it mean? So if you see here, I have 3 time frames, 3 blocks of time. So I have one block here, one block here, and one block here. And in a single block, I have color-coded the transmission reception according to the band. And you see that it is the AP in this case is transmitting on 6 gigahertz and 2.4 gigahertz and receiving on 5 gigahertz. This is what I call as simultaneous transmission and reception. In one block of time, it is possible to receive and transmit on multiple lanes. If you go to the next one, even though the direction of the arrows have changed, the transmission and reception is happening simultaneously. If you see that these 2 bands, there is transmission, the reception, and on this, there is transmission. If you go to the next one, these 2 have transmission and this has reception. So this is what will happen. And I would explain a little more in detail here. Take a case where we only have one channel. So we have a transmission. There should be an ACK, the block ACK. And the channel is busy. And then once again, the AP gets time to transmit. It will transmit and you have an ACK and so on. So in effect, the latency because of the channel being busy is represented by this time L1. This is normal operation. Now let's see how the MLO operation can improve in one of the scenarios. So take the case where link 2 is busy initially when link 1 is transmitting, and then when link 1 is busy, since the busyness of this link is finished here, we know that it can transmit on link 2, and so it transmits on link 2 and you have an ACK. And this can continue. Again, the next transmission can be here, and the next transmission can be here, and so on. So what this is doing is the latency when MLO is used is changed. Okay, I'm not specifically mentioning the fact that the throughput is also going to increase, because in a single channel case, the transmission time would be this plus this. In a multiple link case, you have a transmission here, 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 and here. So the throughput is also going to increase. This is one of the characteristics of MLMR STR. And as depicted here, the latency in this scenario is reduced because we are able to use a non-busy link to do the transmission. The next one is MLMR NSTR. So in this case, if you take each time frame, if you see the arrows are in the same direction, which means it can transmit on multiple channels simultaneously, but it cannot receive in this time frame because the transmission is happening. The reception has to happen in the next time frame. And then if there is some transmission to happen, it would happen in the next time frame and so on. So some amount of synchronization is needed to actually do the NSTR way, the non-simultaneous transmission MLMR type. Okay. So we will just discuss the same scenario in a little more detail, the way it happens with messages. So we have transmission, we have an ACK, it's busy, and it can transmit on the other channel, just like how we have seen in the STR case. And the main thing that I would like to point out is the fact that here, if you see here, at this point, the channel 1 is not busy anymore. So there can be transmission starting here if it was an STR case. In any NSTR case, it cannot finish transmission unless this whole thing is complete and even the ACK is received. So we would be actually having more idle time than MLMR STR, and this is represented by this extra time L3. So this is what is to be noted, mainly because we have to synchronize transmission and reception separately on different links. There is a, what I would say, inefficiency in time usage. MLMR NSTR is not popular due to its complexity because, as I said, it needs synchronization. As of now, we don't have any devices in market that support MLMR NSTR. Nevertheless, we should know this. Maybe something will come in the future. The next one, probably the most important one, is what I would call as the EMLSR. So the way EMLSR works is that it has a single radio, so it can transmit and receive only on one channel. Now, for sake of clarity, I have represented the transmission and reception with this color, and the pink color is used to depict control. So how does this work is that in the client or the AP that has more than one antenna, it's possible that they have another scan radio or something else. It's left to the implementation. But what is required for it to qualify as enhanced, MLSR is the fact that the device should be capable of receiving control frames on the other link when transmitting and receiving on the current link. When I say control frames, I would come to a little more detail later, but it includes channel assessment, check whether the channel is idle or not, and reception of RTS, CTS, MURTS, and so on. These frames in the specification are called ICF, initial control frames, and they are low data rate, so it would not need complex DSP to actually receive those frames. So in effect, reduces the complexity needed, even though it is more complex than MLSR. It is supposed to be an inexpensive when compared to MLMR STR. Now let's see how the signaling works. Again, I just did not mention it. In each time frame, there can be transmission and reception on only one link, and the control reception or transmission on the other link. So this is the normal case where we have a single link. There is there is transmission here. It is busy. Then it again transmits, and then it's busy. I mean, just to mention, all the other I don't know, there can be SIFS or whatever is needed to actually transmit. All these are implied. I did not get into it mainly because they're not really relevant to the current discussion. Now, this is a single link case. How does the two link case work? Just before that, it's the same latency that we have been showing in all the other slides. So you have the two link case. So first, there is transmission on link 1, and there's an ACK. At this time, the channel 2 was busy, so nothing much to do. Now, the channel 1 has got busy, but channel 2 is idle because the busyness got over here. And so what do we have here is that in this case, the AP sends an RTS and the client has to reply with a CTS, and then the transmission can happen. So how this is working is that since the control frame reception has to be allowed on the other channel, or that is the capability of the device, the RTS frame is received on channel 2 by the client, and the client prepares to switch the channel. So it has time because it has to wait for some time, send the CTS, and then there is some gap, and then only it has to be ready for reception. So this sequence is allowing the device to switch to the other channel, and hence give the capability of reducing the latency by using the other channel, even though there is some amount of extra signaling that is here. This signaling, as you may be aware, is not there in the case of MLMR STR. Now, this just continues further because the busyness of this channel is completed here. So you can actually send an CTS sequence there and transmit and wait for an ACK and so on. So this can continue, however long there is data to be transmitted. So EMLSR in some way is kind of bypassing the requirement that you need the second radio by intelligently using this messaging. And obviously it adds some delay, but still it provides lower latency. And, this is how it is represented. So the L2 in this slide will be surely greater than the L2 in the MLMR STR slide, but it is not so much. Now, the last one, the MLO type MLSR, in this, it's very simple. In each time frame, we can only transmit or receive. So this is what happens. And this is very easy, but the main thing is how does it switch? So we have transmission on link 1, there's an ACK and it is busy, and link 2 was also busy. I mean, that's how I did the example. And once the link 2 is available, what the client has to do is send a sleep event on channel 1 and a wake up event on channel 2, and then send the data. So MLSR uses the traditional power management bit that is normally sent in null frames, QoS null frames, to actually sleep and wake up. And hence, it is far slower than EMLSR, but all the same, there is a possibility of channel switch and improvement of latency. I would say there would be a lot of MLSR devices in the market, at least initially, because, MLO as a technology is maturing. People are still discovering things. They're testing and making it work. There are interoperability issues and so on. So initially, MLSR would provide the easiest way to actually satisfy the requirement of MLO. And so because of its lower complexity and cost, there will be a lot of MLSR devices in the market. I think this is my opinion on this case. So this completes the theory part of the MLO. Now we would introduce some definitions. I do not know if you have noticed. So in each of these previous slides, I have named AP as APMLD and the station as non-APMLD. So there is this fundamental change in the way the client and the AP are addressed. AP not so much because we are still calling it AP with an additional name, which is AP MLD. But the station, traditionally that was called station or STA, is now called the non-AP MLD. There are reasons for this, so I will just discuss that in the next slide. Now, MLO defines a set of procedures that allows communication over multiple links between MLDs. MLDs are the whole device as such. What is to be noted is also that the MLD manages the communication over multiple links. As we have just seen before, that there is a messaging, or there's a protocol to switch links or use both the links, and so there is an amount of intelligence that is needed in the MLD to manage the links. Now, the next slide actually gives you more information on why the word non-AP MLD has come. Now, each link is actually called an STA. So this is the departure from what happens earlier. Now, we also have a MAC address for each of the STA. This is obvious because each link is an independent MAC entity and also an independent physical layer entity. So a MAC address is needed. And they also associate a link ID with it. So there's a link ID and a MAC address for each of the links. The STA profiles, that is the details of the links, these will be signaled in probe response and association response by APMLD. As you may know, probe response is normally sent to a client when the client sends probe request, and it can be unicast or broadcast. And if it is sent unicast, it is likely that the STA profiles are included in probe response for the client to know what other links are available other than the current link on which the probe request has been sent. Similarly, association response kind of defines what other STAs profiles is the AP allowing the client to associate to. So it is possible that there are lesser number of STA profiles in the association response than what has been requested by the client or what the AP is capable of. Okay. The non-AP MLD, needless to say, would also indicate the support, that it supports MLO or multiple links in probe request, which is a message that it has to send out to actually associate. And finally, even in the association request, because association request contains all the capabilities in the correct form. The most important thing that needs to be noted here is the fact that MLD also has an associated MAC address. This is the complexity that has been introduced. It is needed. You will see why. So we have a two-level MAC addresses. We have the link MAC addresses, which are called STA addresses, and we also have a MAC address associated with an MLD, the whole device as such. And this would be used in calculation of PTK in a four-way handshake. And this would be the MAC address that would be visible externally. You should be aware that traditionally we had the same MAC address that is used on the Wi-Fi link and in the data that is sent beyond Wi-Fi to the wider world, in case the AP is in bridge mode or the client is sending some data, so the client has a MAC address which actually was matching with the link address. Now this is actually changing. So what are the effects of this? Now, if you have Wireshark and you don't have the correct version or patch for it, you may not be able to decrypt the data packets, because even though four-way handshake is there in the trace, because traditionally they were taking the transmitter addresses for the PTK calculation, and now somebody has to change the code to take the MLD address. So you should keep this in mind when MLO is used. Also, the way you filter packets to see what you want also changes, mainly because you need to now know the link addresses. So if you have a trace, you need to know the 5 gigahertz link address or the 6 gigahertz link address, and then you may have to filter it. One more thing I would like to add is that because of the introduction of MLO, if you would want to debug anything, you would necessarily need a multi-band sniffer. Your sniffer should be capable of receiving on multiple bands, or you use multiple sniffers which are set to different channels and get the traces and probably merge them if you would want, or even analyze them separately. So this is actually becoming or has become a requirement to analyze multi-link operation traces. Having said that, this needs to be what I would say illustrated a little more clearly, because if you would want to see the traces, this is really needed to be understood. So I have AP MLD on the left-hand side and the non-AP MLD on the right-hand side. And the transmission and reception in this case is happening on 2 channels. For the sake of simplicity, assume that they are 2-link capable and they are MLMR STR. It doesn't change too much, even if it is EMLSR or something else, but it just to make the argument simpler. Now, each channel is associated with one STA, and this is called STA1 and this is called STA2. And each of them will have one address. The first one I would call it as AP MLD link 1 address, and the second one I would call as AP MLD link 2 address. Now, the main thing to note is that there is another device, or you can call it as a soft device, which is called MLD, and it has a MAC address. This is the main difference. And as indicated here, the MLD is what is used for transmission over LAN, if at all, for whatever purpose it is done. So for all practical purposes, the MLD would be visible to the outside world. The link addresses should not come into play. It is possible that some device may implement MLD in such a way that these 2 addresses are same, but in general, that's not going to be the case. So please note, it's allowed, but the MLD MAC address would be different from the link addresses in most cases. This is just a mirror image of the AP MLD. So we have another link address here. For link 1, we have for station 2, which is on channel 2, non-AP link address 2. And then we have a non-AP MLD MAC address. What happened here is that traditionally we just had one MAC address for the AP MLD, I mean, assuming one channel, and one MAC address for the non-AP MLD or the client MLD. Now we have 6 addresses. Obviously, the number of channels has increased, but with the introduction of MLD, the additional complexity and the additional MAC addresses have been introduced. If you would want to note, the DHCP would go with MLD MAC address. The DHCP discover would go with MLD MAC address. So because it's a message at a different level, right? I mean, it's actually going to get an IP address. So the IP address would be actually associated with MLD. So if there is application data, this would actually go with MLD address. I think this is something that you need to see. Having said that, we will now, in the next few slides, we will jump into the trace. I have collected some screenshots of traces for ease of use. And so we'll start. How do you identify an MLO AP? It's very simple. you need to check the beacon or the probe response for multi-link IE. So this is the tag. It's called multi-link here, as I have highlighted it. If there is multi-link IE in the beacon, it implies that the AP is capable of MLO. Now, what is there in this multi-link IE? Here it is. The most important parameter that I would like you to note in the multi-link IE, so I have expanded it here, is this parameter that is called maximum number of simultaneous links. In this case, it is given as 2, but the interpretation from the specification is that if this is 2, the total number of links supported by the AP is actually 3. So you need to add 1 to it because even when this number is 0, it means it supports 1 link. So that's how the interpretation for the specification is. So this is the most important parameter to check. In this case, the AP is actually supporting 3 links, 3-link MLO, MLMR STR. The next thing to check is probably whether it supports EMLSR. So there is this IE that is called EML capabilities. It's a bit map, and 1 bit is assigned to say whether EMLSR is supported by the AP. And in this case, in the example that I took, the EMLSR is supported by the AP. Note that there is an MLD MAC address and it is ending with 015601, and this is also signaled in beacon. This is something that was never there. I mean, this kind of information was never available in beacon. What you need to be aware also is that all this come under what we call as common info. Typically, the common info refers to, I mean, apart from the fact that it is giving all this information, it refers to the current link. So the current link is actually link 1. There is a link ID associated with each of the links, and this is done at AP configuration time, not the client. And so the current link information is usually here in the common info. Now, all the information that is actually in the beacon that we have seen here, this actually belongs to the current link. The information for other links is available only on probe response, which I would expand in the next slide. So if you see, there is a parameter called basic STA profile count, and it is given as 0. This is left to the AP implementation. It is possible that the AP can give all the STA profiles here, but it is not mandatory. It will be sent in probe response and association response, as I told before. Now, how does, this is a trivial question, I would say, how does client indicate capability? Client will also send multi-link IE in its probe request and association request. Now, I have expanded the probe response in this slide. So here, if you see this AP, as in the example, has capability of 3 links simultaneously. The first link is 2, then there's a link ID 0 and link ID 1. And if you see, it also supports EMLSR, and I purposely did not expand the other fields because I would want to show you this. And so if you expand this, you will actually get a full-fledged IEs that like how the way you see here. Okay, so what this means is that the probe response would be heavy. It would contain information about the other STAs, because see, the word STA itself means the whole thing. So it will contain information on what bandwidth is used on the other channel, what are the capabilities, in VHT capabilities, HE capabilities, everything. So every link information is contained here, and hence the whole probe response is actually heavy. The outer level on which this probe response is sent, that information is for this link, on which this has been transmitted. Okay, so MLD MAC address is also available in probe response. It should be possible for us to derive all the information, including channel numbers, from these STA profiles. please note that if there is, if you are aware, there is a RNR IE that is also possible to be present, and you may be able to derive, but that is more like an indirect way to derive the kind of links that this AP supports. The straightforward method would be to actually use these STA profiles. This is association request from a client, and in this case, the client supports two links, because if this is one, we need to add one, and so it supports two links. It has this MLD MAC address, and it is giving the STA profile of the other link, which it is not transmitting on, in an additional IE per STA profile. And if you expand this, you will get the whole list of IEs that the client is sending to the AP, which is in effect the capability of the other link for which the transmission is not done. Now, the next one is association response. I don't think we need to go through this in more detail. So this is supporting two links. And so it's actually associating in actually only two links. So sorry. So it supports three links, because 2 + 1, we should say 3, but it is only associating on one additional link other than the current link. So this link ID is 1, and this link ID is 2. And so the association is happening for two links, even though this AP is capable of 3 links. So it can be any reason. The client is only capable of 2 links, or even if client is capable of 3 links, for whatever reason, the AP can associate with lesser number of links. Now, this is how the MAC addresses would look for a case where the association is happening. So link 1 address is the transmitter address in the association request. This is ending with 796CC1, and we have the MLD MAC address F76CC1, and we have the other MAC address here, which is ending with 786CC1. So you understand, one is 796CC1 and one is 786CC1. So please be aware, even though they look same, they will be different. So this is how you get both the link addresses. Now, similar stuff for AP. So we have for the second link 015877. For the first link, we have 015878. This is differing by only 1 bit. Then we also have the MLD MAC address, which is totally different. So this is how you get the MAC addresses that you would need for filtering or for debugging or analysis later. So the next topic I would say is MLO switching, because MLO is about managing two links, and so there should be some way to manage these links. So the first case is MLMR STR. Even though MLMR STR, you understand that the reception and transmission can happen on both the links simultaneously. The way it works is that the transmitter, whether it's a client or an AP, determines which link to use based on a proprietary internal algorithm, possibly based on the congestion at this point of time on each of the links, and also the bandwidth, and also the amount of data that is needed to be sent. So they would decide this in the software, and then the transmission happens on the link or the desired link. Since the receiver is always on for both the links, unless one of the links goes to sleep, so it is possible to do this transmission so easily. So there is no additional signaling. It can just transmit on the other link just like that. I showed a typical trace here. So we have transmission on channel 48, which is the 5 GHz channel. And then there's a block ACK, and then there is a transmission on channel 37, which is 6 GHz. I did plot this IO graph from a real world trace, where I am depicting the red line for the data on 6 GHz and the blue line for data on 5 GHz. And you see that there is data going on these two channels simultaneously throughout. So this is a typical case of MLMR STR. The next one is EMLSR. Here again, The link selection is again proprietary. The difference is that the AP or the client should send an RTS CTS sequence. And so once the CTS is received, the data will be sent on the link. If you see here, I have depicted the same thing in a IO graph from Wireshark. So what I see, what I'm showing you is that there is this notification called EML notification. This is kind of necessary for certifying EMLSR. It's an action frame. It is called EML operating mode notification. This needs to be sent by the transmitter with the EMLSR mode true before the switching happens. Even though it's kind of not really mandatory to make it work, but this is how it is defined. Below is a trace, a simple trace where the data went on 37 channel, which is for the 6 gigahertz. Then we have a MURTS CTS sequence and followed by data on channel 40, which is 5 gigahertz. So this is how the switching happens, and this is how the trace looks if you have a EMLSR capable AP-MLD and non-AP-MLD. Now, the last one, MLSR, even though in this graph, IO graph, I'm showing that the client has actually started transmitting on 5 gigahertz, even when 6 gigahertz transmission is still there. This is mainly due to the fact that the time frame for the x-axis is very high. If I go down and actually see in depth, for each 1 millisecond, the way it works is that I have some data on 6 gigahertz, there's data on 6 gigahertz, then I have a notification, or this is a sleep event on 6 gigahertz, and then it follows up with a wake up event on 5 gigahertz, and then the transmission happens on 5 gigahertz. So this, as I said earlier, it uses the power save bit of the power management flag for the QoS null frame. What is to be expected practically? So now this chart shows who's doing what. MLMR STR would provide higher throughput and lower latency. MLMR NSTR also would provide slightly higher throughput, and probably it will perform a little less compared to MLMR STR. EMLSR would provide lower latency, but no increase in throughput. MLSR would also provide some increase or some advantage in lower latency, but no increase in throughput. The legacy client obviously is behind MLSR. So this is what is expected practically. This is the set of clients that support MLO. So there are other phones, probably Android phones, that are not so popular, but you can note down this if you would like to test with MLO in some way as part of your project. This would summarize what I would call as benefits and challenges. We need to note that there is obviously increased peak throughput for MLMR STR because it is transmitting on 2 links, and there is reduced latency in case of both MLMR and EMLSR because of the way the channel switching happens. When the other channel is busy, we're able to utilize the different channel to gain advantage on this. Then we also have improved connectivity, as band steering would become redundant, because if you get associated in 2 links or 3 links, as it may be required, we don't need to use these traditional proprietary methods to steer the clients to a different channel because this channel is too busy, or there are too many clients, or it is for overall efficiency of the deployment. The fourth one I would like you to note is that mesh backhaul can be a use case for MLMR STR because this is a static use case, and it also needs the higher throughput that MLMR STR may be able to provide in real life. So this is something that you should note. The challenges, I would say, there can be problems on asymmetric links. When I say asymmetric, different bandwidth and congestion on different links would necessarily not give you great throughput with TCP, because TCP is an ACK-based mechanism, and this is likely to take a little more complexity for it to work. So you should note that. Then the complexity of MLO might lead to poor support in market. So we need to see how this is actually evolving. The other suspect things are, if large number of clients are there, would there be a latency improvement? It's not clear at this point. So there should be more tests done on this. We should also be little aware whether the presence of MLO might degrade the performance for legacy clients. For this also, we should do some tests. So we plan to do these tests in future, and we would come up with the results and present it sometime later. So with this, I would bring to an end the theory and the practice part that I wanted to present. And we can take some questions for whatever time we have. Does MLSR mean two channels on the same radio? I would like to put it a little differently. So there is a single radio, but due to the capability of the fact that it has more than one antenna, there is a capability to receive control frames on the other channel. So it is a single radio for all practical purposes, but for reception of low data rate ICF frames, IC frames on the other channel. So it is two channels on the same radio, but not at the same time really for both for data. The next question, will the MLD link MAC share the same OUI as physical MAC? This is left to the implementation, I would say. So there is no requirement from the specification on what MAC address can be used. It is up to the manufacturers. But if you would want to advertise your OUI, I think it's the right thing to do. I'm expecting people to kind of standardize this in some way later, but as of now, as I showed in the traces, I've seen all kinds of MAC addresses, some of them not using their own OUI, which I think is a little bit strange. So then the next question is, it was said that link selection is proprietary. Does that mean each chipset vendor will decide the link selection algorithm? Yes. I would like to point out that, as I was telling, even though it's not mentioned in such big way, because most of our traffic is TCP, we need to be careful on the way we select the link, because TCP is an ACK-based mechanism, and the way we switch channels should not affect the way the ACKs come and reduce the overall throughput. So it is possible that it is better to transmit on a single channel or link if given some environment, and which would give higher throughput than using two links. We have seen practically that sometimes in some scenarios, if you use two links, the overall throughput is actually degraded. The second thing that needs to be taken care by the chipset vendor is the amount of data that is there for all other clients. Again, I'm telling this from the AP point of view. The AP has probably hundreds of clients to manage. So, and some of them are legacy and some of them are Wi-Fi 7 clients. So now AP has to decide this algorithm really cleverly. So I think as of today, this is really work in progress. It is proprietary, and I think it will take some time for this to mature. So I'm not expecting MLO to give all the benefits on day one, especially with slightly larger number of clients. Meaning, I'm not talking about 2 to 4 clients, but let's say you go to 10 clients, probably it is going to be very difficult. There was another question whether MLSR can imply 2 channels for 5 gigahertz itself. The standard itself does not say anything about whether the two channels have to be on the same band or not. I probably see some probably devices that may use two 5 gigahertz channels. But initially, I would think that they would be on different bands. OFDMA, MU-MIMO, and MLO, how can it handle? So all this is at the next level. So OFDMA, MU-MIMO is at the almost the 5 layer. There is an allocation for multiple devices of non-AP MLDs and so on. So the MLO is talking about a slightly higher level. Then do we have something else that I did not answer? Which chipset vendors have got MLO working as of today? I have shown the client chipset vendors list. And as far as AP is concerned, all of them have got MLO working. That's what I believe, and we have seen it. So, but client support for MLO is just coming up. So you see that the most expensive devices are supporting, but let's say the other ones are just waiting to see when whether they have to really do it or not. And I expect some IoT devices, etc., even though if they're Wi-Fi 7 capable, probably will not support MLO. Okay, so having said that, if I have another question here. So how is the primary link decided? This is one of the questions that has come before as well. So the primary link is the link on which the association is happening. And we don't want to say, but it is proprietary. I mean, it's the client that decides which link the association has to be sent to. And clients have their own algorithm to either send on 2.4, or some clients prefer 5 gigahertz. Maybe the newer clients prefer 6 gigahertz. So the link on which the association request is sent is dependent on the client and not the AP. Okay, I think that kind of completes all the questions. Okay. So thanks for joining the webinar. Since we have completed everything on time, I would like to also thank my team, which has made this webinar possible. And we will come up with some kind of experimental results and a new webinar sometime